Hello chemistry students. In the last video we were looking at electron configurations and electron orbitals, and we were exploring the idea that there were patterns and trends in the periodic table. In this video we're going to explore some more of those. So first off, quick recap. We did look at this in the previous video or two, and what we saw was that the periodic table was structured and arranged in a way that helped us to see that there were different orbitals of different shapes and that they sort of existed in these groups. They have been strategically grouped together to reflect this. And so we had our S block, our P block, our D block, and our F block, all of which were related to different orbital geometries. But there are more, and I'm going to look at them today. So first off, this may be something that you've seen before in previous years, but there are different kinds of elements, and they can be categorized mostly as metals and non-metals, but we also have these metalloids, or also known as semi-metals, which sort of sit in between the metals and the non-metals, and they have properties maybe of some, or a little bit of metal properties, a little bit of non-metal properties, and they kind of behave as both at the same time. Now, this isn't something that's specifically a part of our course, but I thought that this would be the most appropriate time to look at it. Now, there are different properties for metals and non-metals. Metals are shiny, have high melting points, are good conductors of electricity and heat. They also have high density, and they're malleable, which means that they can be bent into shape, and ductile, meaning that they can be drawn into a wire. Whereas non-metals are essentially the opposite of all of those things. They're dull, they don't have a very high melting point, they don't conduct electricity or heat very well, they have low density, and if you try to bend them or draw them out into a wire, they break. They're known as brittle. Another thing that we can look at on the periodic table is that we have different states of matter at room temperature, depending on what the element is. Now, almost all of the metals are solid at room temperature. Anything that's gaseous would be considered a non-metal, and they are these ones over here. Our semi-metals are also solid as well, and we have some non-metals that are solid at room temperature as well. Now, there are only two elements that are liquid at room temperature. That's bromine, which is a non-metal, and mercury, which is a metal. Now, when I was looking at this as well, I was thinking to myself, I swear that there's a third one that gets named as a liquid as well. And so I was doing a little bit of hunting and found that gallium was the metal that I was thinking about, and its melting point is at about 30 degrees. Cesium is similar as well, but cesium doesn't really exist naturally. It's a highly reactive metal, so it wasn't really the one that I was thinking of. But at normal room temperature, that metal wouldn't actually melt, it would be solid, but our body temperature is just over 35 degrees, so it's well over the melting point of gallium, and so as a result, if you were to put gallium in your hand, it would melt. Now, I highly recommend that you do not do this yourself, but I thought it was a cool picture and a cool idea to share with you nonetheless. Next thing I want to look at are valence electrons. Now, these are the electrons that exist on the outermost parts of an atom. So for something like a group 1 or group 2 element, this is not something that I think I've talked about before, but groups are essentially our columns. So for a group 1 or group 2 element, their final electrons sit in this S block. So if it's in the first column, as we've sort of already seen before with our electron configurations, it has one outer level or one outer electron, and that sits in the final s orbital. And if it's in the second column, it's there are two outer electrons. Technically, these groups over here are 13, 14, 15, 16, 17, and 18. Sometimes you might also see them labeled as group 3, 4, 5, 6, 7, 8. But technically that's incorrect because we do have the D block in the middle. Now, the D block doesn't feel any sort of pattern in terms of valence electrons. That's why we left them blank. Usually they're positive in charge, positive 1, 2, or 3, but there's no rhyme or reason or pattern to it. So our guys over here that start having electrons in the p block will have first their s shell filled, and then the additional third, fourth, fifth, sixth, seventh, or eighth electron exist in that final p block. And so essentially we're going to be using this valence concept when we start looking at bonding a little bit later. And when we're looking at valence, what we're looking at are the number of electrons on the outside in the final s and or p block, which can be available to exchange or form bonds or react in some way, shape, or form. But main idea here, let's say we have something in this column here that's labeled number 5. It would have 5 electrons on its outer shell, 2 in the s block, and the final 3 from the p block. This sort of brings us into some more interesting periodic trends. So the one that I'm looking at here is atomic radius, so the rough size of the atom. Now what we will see is that the radius of an atom decreases as we move across what we call a period. So again, groups are columns going down, periods are our rows. So as we go across a period, our radius decreases. Now the reason for that, as I've put up the top, is that there are an increased number of protons as we go across. So for example, lithium has 3 protons, whereas fluorine has 7 here at the end. And so the radius decreases because all of those electrons are sort of sitting at that same level, or that they sit a certain distance away from, or they're at a similar energy level as each other. But those electrons that we have there are being attracted by more protons sitting there in the center. So if there's 7 protons pulling all of those outer electrons versus 3 electrons pulling the outer electrons, that the 7 are going to win out and be able to pull all of those electrons closer together. Now what we also see is that the radius increases as we move down one of our groups. And the reason for that, and the term that I've used there, is increased electron shielding. Now that's something that I'm going to explain here really quickly. Now the idea is, as we move out in our energy levels, what's going to end up happening is that the electrons on the outside are not only going to be attracted to the nucleus in the middle, which is positive, but it's also going to be repelled by other negative electrons. So again, concept or idea being, the more electrons that there are between the nucleus and the outer electron, the less the nucleus is going to be able to attract those electrons towards it, which means that the electrons can sit a little bit further out and be spaced further out as well. And this is what we see here in some of our examples when we've looked before at the idea that our s or our p or a d or our f orbitals increase in size and space as we move up our energy levels. It's sort of explained here when we start looking at this electron shielding concept, and that the electrons will sit further and further out because they're being repelled by the electrons themselves. And so thus we end up getting this increased electron shielding pattern here. Now this idea of electron shielding will be applied to a couple of the other patterns that I'm going to be looking at in a minute. We can also graph these atomic radii, and you can see that they follow a very similar pattern as we move through each group, going from our group 1 element, which is always in red, and comparing that to our group 7 elements, which are all here in blue. Hydrogen is just the beginning, so it sort of sits at the bottom. I wouldn't worry about that one too much. So if we start looking at this idea of first ionization energy, first thing we need to know is what that actually means. So another pattern that we can look at is first ionization energy, which means the energy that's required to remove a single outer electron. So if I had an atom and I wanted to remove an electron from it, that's going to require energy for that electron to be able to escape the pull of the nucleus. Now, it takes more energy to remove an electron, or an outer electron, sorry, as we move across a period. Now that's because, similar to what we were talking about with atomic radius, there are more protons in the nucleus which can attract and pull that electron, meaning that you need more energy to remove it. Now, the ionization energy also increases as we move up a group. That's because there's decreasing electron shielding, which means that as if the outer electron is closer to the nucleus and there are less electrons in between, what that will mean is there will be more energy required to pull the electron away from the nucleus. If you have something with a really large amount of electrons, a really big shell, and those outer electrons are really far away, and there's lots of electron shielding going on, those electrons don't require a lot of energy for it to be ionized or for it to be removed from the atom. Again, we have a similar graph sort of showing this pattern in a little bit more detail as well. Almost the opposite, but not exactly the opposite, is this idea of electronegativity. Now, the idea with electronegativity is that it's the ability of the atom to attract electrons and form bonds. So in a sense, it's the opposite to the ionization energy, which is looking at the electron moving away. Here we're talking about electrons going to an atom, or being attracted to an atom, and being able to form bonds. Now you'll see that they both have the same increase pattern, and this is because instead of talking about the amount of energy required for the electron to go away, here we're talking about the ability of the atom to pull in electrons. So that the pattern still looks the same, and it's because of the definition and the distinction between the definition of first ionization energy and electronegativity. But what we'll see is, again, as we increase the number of protons as we go across a period, we'll increase the ability for an atom to attract an electron. If you have more protons in the nucleus, an element is going to be more able to attract an extra electron towards it. And then again, there's increasing electronegativity as we move up a group, because there's less electron shielding, which means that those protons in the nucleus are more able to attract an electron, because there aren't as many electrons interfering with those protons in the middle attracting an electron. Now, two things to note. One I've got written here is that D block elements don't vary much across the periods. Again, they all don't have much of a pattern. They don't have really any rhyme or reason as to why they do what they do, in the same way that our S or P block elements do. Similar to what we were talking about with our valencies before, or the number of valence electrons that we have. Something else to note as well is that noble gases don't really have an electronegativity, because they already have a full outer shell, so they don't actually like to pick up any additional electrons. That will make a little bit more sense when we look at bonding in the next couple of videos. Now, the last one that I want to show you is reactivity with water. And so if you're looking at the ability of an element to react with water, what you're looking for is either the ability to get rid of an electron and give it to water really easily. That will help to form bonds or new kinds of particles. And the opposite to that is something with really high electronegativity, something that's able to rip electrons off of a water molecule. And essentially what that means is, again, make new bonds, cause a reaction to happen. Both of those kinds of elements are really, really, really good at reacting with water. So what you'll see is that for metals, really reactive metals have low ionization energies here. So ones like these. And for non-metals, what we have are really high electronegativities, things that can pull electrons in really easily. Both of these kinds of elements are very reactive with water. And again, noble gases don't do a lot of reacting because they have full orbitals. And as well, our transition metals that exist in the D block in the middle have a similar concept as well, where they don't really behave particularly different to each other. Now that's going to conclude our video for now. What we're going to be looking at for next lesson is we're going to be starting to look at bonding in molecules, which is going to build on some of the things that I've already alluded to today. Thank you very much, and I'll catch you in the next one.